let's get right to our first subject. It concerns the kind of weather that made Judy Garland famous.
Toto, I have a feeling we're not in Kansas anymore.
Wouldn't it be nice if tornadoes could safely fly us over the rainbow? Unfortunately, tornadoes are one of nature's most deadly storms. And Paul Barassa of Lowell, Massachusetts wants to know why. He writes, what makes tornadoes so dangerous? Well, let's put the question to an expert, meteorologist Fred Gadomski from Penn State University. Fred, what makes tornadoes so deadly?
Well, Ira, the winds in tornadoes range from 100 to 300 miles per hour. And that can make ordinary objects do pretty extraordinary things.
You know, I did hear about cases where you have pieces of straw going through wood or being embedded in fence posts. That really happens?
These are not stories, Ira. In fact, why don't you hand me a toothpick and we'll try to show you that this can happen.
What are you going to do here?
Perfectly ordinary. We're going to put this toothpick in this machine which can create a 300-mile-per-hour wind.
No
Down
kidding.
at the other end of the machine is a pine board, which is going to be the target. You never want to be a target in a tornado.
Not me.
Okay,
I'm standing out of the way. This looks dangerous.
300-mile-per-hour wind. Are you ready?
Go ahead. Look at that. Look at that. Can you see that? You can see this, that you pull the wood out. The toothpick went right through the wood, inside and out. So it's not just the wind that's the problem in a tornado, it's the stuff that's flying around in the wind.
Right. The debris may be one of the worst parts of a tornado.
All right, let's talk about tornadoes. How do you get a wind to go that fast that you can put wood through wood like that?
Well, it all has its roots in the spin. Spinning is the key, Ira. And we have a demonstration back here, which is just a tank which has water in it that's already spinning. It's being stirred. And why don't you add a little Alka-Seltzer for me so we can actually analyze the motions.
Make some bubbles, huh?
What's going on in this vortex. And note the bubbles out near the outside.
Yes, they're spinning kind of slow, lazily going around in a circle.
But as they make their way toward the inside, they really get concentrated into a much faster spin. In fact, you see a little vortex in there.
Oh, yeah.
Why don't we add some food coloring and analyze the motion within the vortex itself?
So it's like the funnel coming down from the cloud.
Very much like what happens in an
that.
actual thundercloud. You bring the tornado down to the surface and it touches down eventually.
So you really then are concentrating the wind by bringing it from the outside in a slower motion and concentrating in the middle of a rotating cloud.
That's absolutely right.
Well, what kind of conditions in real life do you have for all of this to happen?
Well, all tornadoes begin with apparent thunderstorm. And in fact, we have some footage which shows the development of a typical thunderstorm in time-lapse photography.
They're really billowing up those clouds.
That's right. What you're seeing is warm, moist, humid air starting to rise in almost an explosive manner. It's the updraft that drives the thunderstorm and creates the really nasty thunderstorms, big updrafts extending some 5–10 miles into the atmosphere that really do the job. It's a thunderstorm like this that can turn into a tornado.
Well, look at that one. Now, how come you have these violent tornadoes only in certain parts of the country?
Well, and in fact, the central part of the United States is the most tornado-prone place in the world.
Tornado Alley, they call it.
That's right, and it's really an accident of geography. Warm, moist air from the Gulf of Mexico, a good supply of that, with cold, dry air ready to come in from the mountains to the west. That really is the kind of conditions you need.
Right, you gave us the ingredients, you told us we have a thunderstorm, but that's the air that's rising up. How do you get the air to go around in a circle to form the tornado?
Okay, here's a parent thunderstorm, here's its updraft. What you need is the wind direction to be different in different parts of the thunderstorm. One wind direction here, another one here, another one here, and that can get that updraft rotating into something we call a mesocyclone.
Mesocyclone.
It's the beginning of a tornado.
I see. Is that the point yet where you issue a tornado warning or a tornado watch or something like that?
If we can find a mesocyclone, we will issue a tornado watch, warn people in the path of this thunderstorm.
But you got to find one. I mean, how do you know when that condition is happening?
Well, we have a nifty tool these days called Doppler radar.
I've heard about that.
In the old days, all we had was radar that showed us how much it was raining. Light rain here, heavy rain here. But with Doppler radar, we have the ability to actually see the wind. And you've got here red showing one direction of wind, blue and green showing the opposite direction, and that really is the sense of rotation you get there, and that's the mesocyclone.
Is that the funnel cloud we're actually looking at there?
Not quite. You're looking at that big rotating updraft, the mesocyclone. What you have to do is concentrate it. And that's an interesting process. Why don't we make a tornado right here in the
Right here,
studio?
we're going to make a tornado?
You betcha.
Let's do that. I want to see this.
Now this here is a tornado simulator of the kind that might be built in a research laboratory to study the properties of tornadoes.
What have you got here? I see a little town down there.
Any town, USA, and it's about to be struck by a tornado. Up here we have a fan that's a big fan that perhaps your biggest fan, Ira.
Oh, you said it, not me.
That'll create our updraft. And down here we have some vanes which will help the convergence of the winds, and that's necessary to concentrate the updraft.
Right, right.
In the atmosphere, we don't understand exactly the processes that create this convergence.
No, we don't.
And so this is a good way to study some of those properties by changing these vanes around here. So why don't we get the updraft going? And believe it or not, Ira, we've got a tornado in there.
You don't see anything.
Now, in the real atmosphere, you've got debris in the funnel, and you've also got water vapor condensing in the funnel, and that makes it visible to you.
I see. So
Here-
we're going to add some of that stuff, right?
We're going to add some smoke, our own little debris, to make the tornado.
Look at that. That's really impressive, Fred.
It really is. This is a tornado, and by changing some of these vanes here, we could study different properties of the tornado this way.
So what you have is the air is being sucked up by the fan,
Right.
and the veins down here are making it become compressed and form that tight circle which creates the tornado.
That's correct.
And that's art imitating life, so to speak.
That's right. And you're looking at it from an unusual angle from up on top, and an impressive sight it is, but even more impressive is some footage we have that was taken from a helicopter and shows a tornado in action. This was a traffic helicopter.
Look at that.
Yeah, it's an unbelievable sight, really.
It looks almost, you know, it looks like, ooh, that was the flash. That flash.
That
what
was a power line, no doubt being snapped there.
My goodness, ooh.
And there's another and another.
Now it looks like it's moving very, very slowly across the ground.
That's right. Tornadoes can move, an average speed would be 10, 15, 20 miles per hour. So they're not ripping along at 200 or 300 miles like the winds within them.
And you can actually see the debris being ripped up and shredded and torn up from, look at that. And it looks like there's more than one funnel.
Yeah, in this shot, you can see little funnels going around the main funnel.
Right.
And those can have some of the highest winds right in those little funnels.
You can see the destructive force, and you can see why we said before that it's the debris. Look at the debris being thrown around in there. Is this the kind of force that blows houses apart? They tell you to crack the window a little bit in the house.
Yeah, the explosion of the house is a little bit of a myth we've found out. That the pressure difference that might create that explosion really doesn't happen in a tornado. So you shouldn't waste time opening your windows in a tornado warning.
Well, what should you do?
You should head for the basement, get under something pretty heavy to avoid anything hitting you in the head that should be flying around if it hits your house.
And you have no basement in your house.
You go to an interior hallway or an interior room. Often a bathroom is a good room because it's in the interior, and also because there's plumbing around the outside which reinforces the walls and makes it a sturdy room.
That's a good tip. I never realized that. Thank you very, very much, Fred, for this wonderful whirlwind tour of tornadoes. We'll be back with more in just a minute.
More party trivia. Fascinating fact number 234. Yeast. When it comes to healing burns, yeast rises to the occasion. In first-degree burns, ointments that contain yeast will heal wounds faster. The tiny fungi promote development of minute blood vessels, which carry more oxygen to the wound and encourage healing.
Recognize this image. Look carefully. It's a picture of Albert Einstein. The problem in recognizing this face is that to your eye, this picture is just a mass of dots. It's up to your brain to assemble these points into a recognizable face. This is just one example of how vision really occurs in our brains. And nowhere is this principle shown more successfully than at the Exploratorium in San Francisco. That's where we sent field reporter Peggy Knapp.
We're looking at an image of the Exploratorium in San Francisco through this special lens called a Fresnel lens. Now, the real object, the building itself, is actually behind me. The image is made when the lens gathers the light that's being reflected off of the Exploratorium. In fact, everything you see is really light. You could say that you're not seeing me, you're seeing the light reflected off of me. And it's easy to bend light into new patterns. That's why images can fool you.
Images are also subject to interpretation by our brains. For everything we see, our brain plays a key role and provides any missing information. The vision exhibits here show how the eye and the brain work together. Sally Dunsing, the assistant director at the Exploratorium, was my guide.
How do we see? How does the eye work?
Well, let's start with the lens.
All right.
Each of your eyes has a convex lens, kind of like this, and they take the light from the outside world and actually bend it and make an upside down or inverted image on the back of each eye.
But we don't see upside down.
No, and that's the point, because seeing isn't just in the eye, it's in the brain as well. So the brain, somewhere in the brain, the image gets re-inverted, so you see a real image that's actually right side up.
The image on the back of our eye is not only upside down, it's also flat, distorted, full of holes, and out of focus. So our brain has to fill in the gaps. For example, this image is a miracle of eye-brain coordination. A thin wand waving in front of a slide projector reflects this picture to our eyes. Now we'll slow down the motion of the wand, and we can see that our retina is receiving only tiny slivers of the image at a time. But our brain retains each piece and puts the whole picture together. Our brain performs similar visual feats every day. Like a detective, it gathers clues from the patchy evidence our eye receives. Optical illusions can show us how our brain solves visual mysteries.
Okay, Sally, what's going on here?
Well, this is a painting that's done in proper perspective, but the two curves aren't. They're actually the same size. And this is one way to show you how important size and distance cues are as you interpret what's going on.
They're the same size?
Yes. So stand over there and take a look.
All right, well, it still looks a little out of kilter, but this cow looks larger from here.
And what's happening there is you're actually closer to that lower cow's head, and it makes a bigger image on the back of your eye, so it kind of cancels out the illusion.
Oh, I see.
And now if you walk over to the left, now you're that much
Yeah.
closer to this upper cow, and what does it look like?
It looks huge.
So the illusion is that much stronger because you're that much closer to this cow's head. Now you measure them.
Uh-huh. Well, they are.
You see, they're really the same size. And so now that you've seen it,
I
you've
still
measured
don't
it.
believe it.